Welcome to the I Can't Sleep podcast, where I read random articles from across the web to bore you to sleep with my soothing voice. I'm your host, Benjamin Boster. Today's episode is from a Wikipedia article titled Electricity. Electricity is the set of physical phenomena associated with the presence and motion of matter possessing an electric charge. Electricity is related to magnetism, both being part of the phenomenon of electromagnetism, as described by Maxwell's equations. Common phenomena are related to electricity, including lightning, static electricity, electric heating, electric discharges, and many others. The presence of either a positive or negative electric charge produces an electric field. The motion of electric charges is an electric current and produces a magnetic field. In most applications, Coulomb's law determines the force acting on an electric charge. Electric potential is the work done to move an electric charge from one point to another within an electric field, typically measured in volts. Electricity plays a central role in many modern technologies, serving in electric power where electric current is used to energize equipment, and in electronics dealing with electrical circuits involving active components such as vacuum tubes, transistors, diodes, and integrated circuits, and associated passive interconnection technologies. The study of electrical phenomena dates back to antiquity, with theoretical understanding progressing slowly until the 17th and 18th centuries. The development of the theory of electromagnetism in the 19th century marked significant progress, leading to electricity's industrial and residential applications by electrical engineers by the century's end. This rapid expansion in electrical technology at the time was a driving force for the Second Industrial Revolution, with electricity's versatility driving transformations in industry and society. Electricity is integral to applications spanning transport, heating, lighting, communications, and computation, making it the foundation of modern industrial society. Long before any knowledge of electricity existed, people were aware of shocks from electric fish. Ancient Egyptian texts dating from 2750 BCE described them as the protectors of all other fish. Electric fish were again reported millennia later by ancient Greek, Roman, and Arabic naturalists and physicians. Several ancient writers, such as Pliny the Elder and Scribonius Largus, attested to the numbing effect of electric shocks delivered by electric catfish and electric rays, and knew that such shocks could travel along conducting objects. Patients with ailments such as gout or headache were treated to touch electric shocks, were directed to touch electric fish in the hope that the powerful jolt might cure them. Ancient cultures around the Mediterranean knew that certain objects, such as rods of amber, could be rubbed with cat's fur to attract light objects like feathers. Thales of Miletus made a series of observations on static electricity around 600 BCE, from which he believed that friction rendered amber magnetic, in contrast to minerals such as magnetite, which needed no rubbing. Thales was incorrect in believing the attraction was due to a magnetic effect, but later science would prove a link between magnetism and electricity. According to a controversial theory, the Parthians may have had knowledge of electroplating based on the 1936 discovery of the Baghdad battery, which resembles a galvanic cell, though it is uncertain whether the artifact was electrical in nature. Electricity would remain little more than intellectual curiosity for millennia until 1600, when the English scientist William Gilbert wrote De Magnete, in which he made a careful study of electricity and magnetism, distinguishing the lodestone effect from static electricity produced by rubbing amber. He coined the Neo-Latin word electricus, of amber or like amber, from electron, the Greek word for amber, to refer to the property of attracting small objects after being rubbed. This association gave rise to the English word electric and electricity, which made their first appearance in print in Thomas Brown's Pseudodoxia Epidemica of 1646. Further work was conducted in the 17th and early 18th centuries by Otto von Guericke, Robert Boyle, Stephen Gray, and C.F. Dufay. Later in the 18th century, Benjamin Franklin conducted extensive research in electricity, selling his possessions to fund his work. In June 1752, he is reputed to have attached a metal key to the bottom of a dampened kite string and flown the kite in a storm-threatened sky. A succession of sparks jumped from the key to the back of his hand, showing that lightning was indeed electrical in nature. He also explained the apparently paradoxical behavior of the Leyden jar as a device for storing large amounts of electrical charge in terms of electricity consisting of both positive and negative charges. In 1775, Hugh Williamson reported a series of experiments to the Royal Society on the shocks delivered by the electric eel. That same year, the surgeon and anatomist John Hunter described the structure of the fish's electric organs. In 1791, Luigi Galvani published his discovery of bioelectromagnetics, demonstrating that electricity was the medium by which neurons passed signals to the muscles. Alessandro Volta's battery, or voltaic pile, of 1800, made from alternating layers of zinc and copper, provided scientists with a more reliable source of electrical energy than the electrostatic machines previously used. The unity of electric and magnetic phenomena is due to Hans Christian Ørsted and André Marie Ampère in 1819 to 1820. Michael Faraday invented the electric motor in 1821, and Georg Ohm mathematically analyzed the electrical circuit in 1827. Electricity and magnetism and light were definitively linked by James Clerk Maxwell, in particular in his On Physical Lines of Force in 1861 and 1862. While the early 19th century had seen rapid progress in electrical science, the late 19th century would see the greatest progress in electrical engineering. Through such people as Alexander Graham Bell, Otto Blythe, Thomas Edison, Galileo Ferraris, Oliver Heaviside, Ányos Jedlik, William Thomson, First Baron Kelvin, Charles Algernon Parsons, Werner von Siemens, Joseph Swan, Reginald Fessenden, Nikola Tesla, and George Westinghouse, electricity turned from a scientific curiosity into an essential tool for modern life. In 1887, Heinrich Hertz discovered that electrodes illuminated with ultraviolet light create sparks more easily. In 1905, Albert Einstein published a paper that explained experimental data from the photoelectric effect as being the result of light energy being carried in discrete quantized packets, energizing electrons. This discovery led to the quantum revolution. Einstein was awarded the Nobel Prize in Physics in 1921 for his discovery of the law of the photoelectric effect. The photoelectric effect is also employed in photocells, such as can be found in solar panels. The first solid-state device was the cat's whisker detector, first used in the 1900s in radio receivers. A whisker-like wire is placed lightly in contact with a solid crystal, such as germanium crystal, to detect a radio signal by the contact junction effect. In a solid-state component, the current is confined to the solid elements and compounds engineered specifically to switch and amplify it. Current flow can be understood in two forms, as negatively charged electrons and as positively charged electron deficiencies called holes. These charges and holes are understood in terms of quantum physics. The building material is most often a crystalline semiconductor. Solid-state electronics came into its own with the emergence of transistor technology. The first working transistor, a germanium-based point contact transistor, was invented by John Bardeen and Walter Hauser Brattain at Bell Labs in 1947, followed by the bipolar junction transistor in 1948. The presence of charge gives rise to an electrostatic force. Charges exert a force on each other, an effect that was known, though not understood, in antiquity. A lightweight ball suspended by a fine thread can be charged by touching it with a glass rod that has itself been charged by rubbing with a cloth. If a similar ball is charged by the same glass rod, it is found to repel the first. The charge acts to force the two balls apart. Two balls that are charged with a rubber amber rod also repel each other. However, if one ball is charged by the glass rod and the other by an amber rod, the two balls are found to attract each other. These phenomena were investigated in the late 18th century by Charles Augustin de Coulomb, who deduced that charge manifests itself in two opposing forms. This discovery led to the well-known axiom, like-charged objects repel and opposite-charged objects attract. The force acts on the charged particles themselves. Hence, charge has a tendency to spread itself as evenly as possible over a conducting surface. The magnitude of the electromagnetic force, whether attractive or repulsive, is given by Coulomb's law, which relates the force to the product of the charges and has an inverse square relation to the distance between them. The electromagnetic force is very strong, second only in strength to the strong interaction. But unlike that force, it operates over all distances. In comparison with much weaker gravitational force, the electromagnetic force pushing two electrons apart is 10 to the 42nd times that of the gravitational attraction pulling them together. Charge originates from certain types of subatomic particles, the most familiar carriers of which are the electron and proton. Electric charge gives rise to and interacts with the electromagnetic force, one of the four fundamental forces of nature. Experiment has shown charge to be a conserved quantity, that is, the net charge within an electrically isolated system will always remain constant regardless of any changes taking place within that system. Within the system, charge may be transferred between bodies, either by direct contact or by passing along a conducting material such as a wire. The informal term static electricity refers to the net presence or imbalance of charge on a body, usually caused when dissimilar materials are rubbed together, transferring charge from one to the other. The charge on electrons and protons is opposite in sign, hence an amount of charge may be expressed as being either negative or positive. By convention, the charge carried by electrons is deemed negative, and that by protons positive, a custom that originated with the work of Benjamin Franklin. The amount of charge is usually given the symbol Q and expressed in coulombs. Each electron carries the same charge of approximately negative 1.6022 times 10 to the negative 19 coulomb. The proton has a charge that is equal and opposite, and thus plus 1.6022 times 10 to the negative 19 coulomb. Charge is possessed not just by matter, but also by antimatter, each antiparticle bearing an equal and opposite charge to its corresponding particle. Charge can be measured by a number of means, an early instrument being the gold leaf electroscope, which, although still in use for classroom demonstrations, has been superseded by the electronic electrometer. The movement of electric charge is known as an electric current, the intensity of which is usually measured in amperes. Current can consist of any moving charged particles. Most commonly, these are electrons, but any charge in motion constitutes a current. Electric current can flow through some things, electrical conductors, but will not flow through an electrical insulator. By historical convention, a positive current is defined as having the same direction of flow as any positive charge it contains, or to flow from the most positive part of a circuit to the most negative part. Current defined in this manner is called conventional current. The motion of negatively charged electrons around an electric circuit, one of the most familiar forms of current, is thus deemed positive in the opposite direction to that of the electrons. However, depending on the conditions, an electric current can consist of a flow of charged particles in either direction, or even in both directions at once. The positive to negative convention is widely used to simplify this situation. The process by which electric current passes through a material is termed electrical conduction, and its nature varies with that of the charged particles and the material through which they are traveling. Examples of electric currents include metallic conduction, where electrons flow through a conductor such as a metal, and electrolysis, where ions, charged atoms, flow through liquids, or through plasmas such as electrical sparks. While the particles themselves can move quite slowly, sometimes with an average drift velocity only fractions of a millimeter per second, the electric field that drives them itself propagates at close to the speed of light, enabling electrical signals to pass rapidly along wires. Current causes several observable effects, which historically were the means of recognizing its presence. That water could be decomposed by the current from a voltaic pile was discovered by Nicholson and Carlisle in 1800, a process now known as electrolysis. Their work was greatly expanded upon by Michael Faraday in 1833. Current through a resistance causes localized heating, an effect James Prescott Joule studied mathematically in 1840. One of the most important discoveries relating to current was made accidentally by Hans Christian Ørsted in 1820, when, while preparing a lecture, he witnessed the current in a wire disturbing the needle of a magnetic compass. He had discovered electromagnetism, a fundamental interaction between electricity and magnetics. The level of electromagnetic emissions generated by electric arcing is high enough to produce electromagnetic interference, which can be detrimental to the workings of adjacent equipment. In engineering or household applications, current is often described as being either direct current, DC, or alternating current, AC. These terms refer to how the current varies in time. Direct current, as produced, by example, from a battery, and required by most electronic devices, is a unidirectional flow from the positive part of a circuit to the negative. If, as is most common, this flow is carried by electrons, they will be traveling in the opposite direction. Alternating current is any current that reverses direction repeatedly. Almost always this takes the form of a sine wave. Alternating current thus pulses back and forth within a conductor without the charge moving any net distance over time. The time averaged value of an alternating current is zero, but it delivers energy in first one direction and then the reverse. Alternating current is affected by electrical properties that are not observed under steady state direct current, such as inductance and capacitance. These properties, however, can become important when circuitry is subjected to transients, such as when first energized. The concept of the electric field was introduced by Michael Faraday. An electric field is created by a charged body in the space that surrounds it and results in a force exerted on any other charges placed within the field. The electric field acts between two charges in a similar manner to the way that the gravitational field acts between two masses, and, like it, extends towards infinity and shows an inverse square relationship with distance. However, there is an important difference. Gravity always acts in attraction, drawing two masses together, while the electric field can result in either attraction or repulsion. Since large bodies such as planets generally carry no net charge, the electric field at a distance is usually zero. Thus, gravity is the dominant force at distance in the universe, despite being much weaker. An electric field generally varies in space, and its strength at any one point is defined as the force per unit charge that would be felt by a stationary, negligible charge placed at that point. The conceptual charge, termed a test charge, must be vanishingly small to prevent its own electric field disturbing the main field, and must also be stationary to prevent the effect of magnetic fields. As the electric field is defined in terms of force, and force is a vector having both magnitude and direction, it follows that an electric field is a vector field. The study of electric fields created by stationary charges is called electrostatics. The field may be visualized by a set of imaginary lines whose direction at any point is the same as that of the field. This concept was introduced by Faraday, whose term lines of force still sometimes sees use. The field lines are the paths that a point positive charge would seek to make as it was forced to move within the field. They are, however, an imaginary concept with no physical existence, and the field permeates all the intervening space between the lines. Field lines emanating from stationary charges have several key properties. First, that they originate at positive charges and terminate at negative charges. Second, that they must enter any good conductor at right angles. And third, that they may never cross nor close in on themselves. A hollow conducting body carries all its charge on its outer surface. The field is therefore zero at all places inside the body. This is the operating principle of the Faraday cage, a conducting metal shell which isolates its interior from outside electrical effects. The principles of electrostatics are important when designing items of high voltage equipment. There is a finite limit to the electric field strength that may be withstood by any medium. Beyond this point, electrical breakdown occurs, and an electric arc causes flashover between the charged parts. Air, for example, tends to arc across small gaps at electric field strengths, which exceed 30 kilovolts per centimeter. Over large gaps, its breakdown strength is weaker, perhaps 1 kilovolt per centimeter. The most visible natural occurrence of this is lightning, caused when charge becomes separated in the clouds by rising columns of air, and raises the electric field in the air to greater than it can withstand. The voltage of a large lightning cloud may be as high as 100 millivolts and have discharged energies as great as 250 kilowatts. The voltage of a large lightning cloud may be as high as 100 megavolts and have discharge energies as great as 250 kilowatt hours. The field strength is greatly affected by nearby conducting objects, and it is particularly intense when it is forced to curve around sharply pointed objects. This principle is exploited in the lightning conductor, the sharp spike of which acts to encourage the lightning strike to develop there, rather than to the building it serves to protect. The concept of electric potential is closely linked to that of the electric field. A small charge placed within an electric field experiences a force. and to have brought that charge to that point against the force requires work. The electric potential at any point is defined as the energy required to bring a unit rest charge from an infinite distance slowly to that point. It is usually measured in volts, and 1 volt is the potential for which 1 joule of work must be expended to bring a charge of 1 coulomb from infinity. This definition of potential, while formal, has little practical application, and a more useful concept is that of electric potential difference, and is the energy required to move a unit charge between two specified points. An electric field has this special property that is conservative, which means that the path taken by the test charge is irrelevant. All paths between two specified points expand the same energy, and thus a unique value for potential difference may be stated. The volt is so strongly identified as the unit of choice for measurement and description of electric potential difference that the term voltage sees greater everyday usage. For practical purposes, it is useful to define a common reference point to which potentials may be expressed and compared. While this could be at infinity, a much more useful reference is the Earth itself, which is assumed to be at the same potential everywhere. This reference point naturally takes the name Earth or ground. Earth is assumed to be an infinite source of equal amounts of positive and negative charge, and is therefore electrically uncharged and unchargeable. Electric potential is a scalar quantity, that is, it has only magnitude and not direction. It may be viewed as analogous to height, just as a released object will fall through a difference in heights caused by a gravitational field, so a charge will fall across the voltage caused by an electric field. As relief maps show contour lines marking points of equal height, a set of lines marking points of equal potential, known as equipotentials, may be drawn around an electrostatically charged object. The equipotentials cross all lines of force at right angles. They must also lie parallel to a conductor's surface, since otherwise there would be a force along the surface of the conductor that would move the charge carriers to even the potential across the surface. The electric field was formally defined as the force exerted per unit charge, but the concept of potential allows for a more useful and equivalent definition. The electric field is the local gradient of the electric potential. Usually expressed in volts per meter, the vector direction of the field is the line of greatest slope of potential, and where the equipotentials lie closest together. Ørsted's discovery in 1821 that a magnetic field existed around all sides of a wire carrying an electric current indicated that there was a direct relationship between electricity and magnetism. Moreover, the interactions seemed different from gravitational and electrostatic forces, the two forces of nature then known. The force on the compass needle did not direct it to or away from the current-carrying wire, but acted at right angles to it. Ørsted's words were that the electric conflict acts in a revolving manner. The force also depended on the direction of the current, for if the flow was reversed, then the force did too. Ørsted did not fully understand his discovery, but he observed the effect was reciprocal. A current exerts a force on a magnet, and a magnetic field exerts a force on a current. The phenomenon was further investigated by Ampere, who discovered that two parallel current-carrying wires exerted a force upon each other. Two wires conducting currents in the same direction are attracted to each other, while wires containing currents in opposite directions are forced apart. The interaction is mediated by the magnetic field each current produces, and forms the basis for the international definition of the ampere. This relationship between magnetic fields and currents is extremely important, for it led to Michael Faraday's invention of the electric motor in 1821. Faraday's homopolar motor consisted of a permanent magnet sitting in a pool of mercury. A current was allowed through a wire suspended from a pivot above the magnet and dipped into the mercury. The magnet exerted a tangential force on the wire, making it circle around the magnet for as long as the current was maintained. Experimentation by Faraday in 1831 revealed that a wire moving perpendicular to a magnetic field developed a potential difference between its ends. Further analysis of this process, known as electromagnetic induction, enabled him to state the principle, now known as Faraday's law of induction, that the potential difference induced in a closed circuit is proportional to the rate of change of magnetic flux through the loop. Exploitation of this discovery enabled him to invent the first electrical generator in 1831, in which he converted the mechanical energy of a rotating copper disk to electrical energy. Faraday's disk was inefficient and of no use as a practical generator, but it showed the possibility of generating electric power using magnetism, a possibility that would be taken up by those that followed on from his work. An electric circuit is an interconnection of electric components, such that electric charge is made to flow along a closed path, a circuit, usually to perform some useful task. The components in an electric circuit can take many forms, which can include elements such as resistors, capacitors, switches, transformers, and electronics. Electronic circuits contain active components, usually semiconductors, and typically exhibit nonlinear behavior, requiring complex analysis. The simplest electric components are those that are termed passive and linear. While they may temporarily store energy, they contain no source of it and exhibit linear responses to stimuli. The resistor is perhaps the simplest of passive circuit elements. As its name suggests, it resists the current through it, dissipating its energy as heat. The resistance is a consequence of the motion of charge through a conductor. In metals, for example, resistance is primarily due to collisions between electrons and ions. Ohm's law is a basic law of circuit theory, stating that the current passing through a resistance is directly proportional to the potential difference across it. The resistance of most materials is relatively constant over a range of temperatures and currents. Materials under these conditions are known as ohmic. The ohm, the unit of resistance, was named in honor of Georg Ohm, and is symbolized by the Greek letter omega. 1 omega is the resistance that will produce a potential difference of 1 volt in response to a current of 1 amp. The capacitor is a development of the Leyden jar and is a device that can store charge, and thereby storing electrical energy in the resulting field. It consists of 2 conducting plates separated by a thin insulating dielectric layer. In practice, thin metal foils are coiled together, increasing the surface area per unit volume, and therefore the capacitance. The unit of capacitance is the farad, named after Michael Faraday, and given the symbol F. 1 farad is a capacitance that develops a potential difference of 1 volt when it stores a charge of 1 coulomb. A capacitor connected to a voltage supply initially causes a current as it accumulates charge. This current will, however, decay in time as the capacitor fills, eventually falling to zero. A capacitor will therefore not permit a steady state current, but instead blocks it. The inductor is a conductor, usually a coil of wire, that stores energy in a magnetic field in response to the current through it. When the current changes, the magnetic field does too, inducing a voltage between the ends of the conductor. The inducing voltage is proportional to the time rate of change of the current. The constant of proportionality is termed the inductance. The unit of inductance is the Henry, named after Joseph Henry, a contemporary of Faraday. 1 Henry is the inductance that will induce a potential difference of 1 volt if the current through it charges at a rate of 1 ampere per second. The inductor's behavior is in some regards converse to that of the capacitor. It will freely allow an unchanging current, but opposes a rapidly changing one.